actually started on at 10 this time. It's the first time that I've done that in forever. Well, welcome to another stream. Today we're going to be looking at a very cool algorithm, in my opinion. It's one of the more interesting ones I've delved into. I can already see that in chat that someone named Your Name Here has said hype, let's go. I appreciate the anticipation for another testosterone-filled stream. So alright. So I was just thinking of going through a little bit of an overview of what the algorithm actually is, and then we'll go through, I guess, how to write it in C++. So let's just go ahead and alright, so let's get started here. Switch on the desktop. Alright, so you might be wondering, well, what is this? So the Perlin Noise algorithm is it was created by Ken Perlin, who is a professor at NYU, at New York University, if you don't know. Oh my god. It's an algorithm, it's a procedural generation, or texture generation, and it works in any number of dimensions. And, well, you might be wondering, well, what is that? So, when you look at this smooth ball here, it doesn't look very interesting, but the bumpy ball, you now see what the purpose of these colors were. However, these colors weren't just taken from any sort of image. I didn't just give this there wasn't just a PNG file that had these colors on there. These colors were generated procedurally, so they were generated at runtime using some sort of algorithm. And it turns out that Ken Perlin created this. He actually did this while he was working on the movie Tron back in the late 1900s. That seems like a long time ago. And he created it to create the computer backdrop, the computer textures in the background, so he wouldn't have to automatic or manually input the height, the depth map. And you see that it creates these effects to the lighting. Like when we in OpenGL, if we get into more advanced lighting techniques, we'll see how this all works out. But it's pretty interesting stuff. So the purpose of it is creating these textures in such a way that they seem to be natural. Like these are textures that you could see on natural objects, like in a bumpy ball. That's what you might see in something like a statue, an old statue. Games use this all the time to create texture for their objects, which will react to lighting in different ways. So yeah, these textures essentially seem to be random, but they're not entirely random. They're pseudo-random. That's the term for it. So let's go ahead and look at this principles of Perlin Noise. So the algorithm in general is very interesting to study. There's a lot of math behind it. I mean, it's not too hard to look at conceptually. But I did have a little bit of trouble, but it turns out that my trouble wasn't with the algorithm, is with my image library, which I'll get to in a second, or once we go over this. So the basis of the algorithm is that it's based on pseudo-random arrays and gradients. So pseudo-random arrays, or tables, I'll say, and gradients. So tables, pretty simple. It's a lookup table, so these are going to be lookup tables. However, gradients are a little bit different. So gradients you can think of as a derivative. However, it's more than just a derivative, because derivative you're usually thinking of dy dx, so derivative of a 2D line. How gradients are derivatives of vectors. So these can be applied to any number of dimensions, just like this algorithm is. So you have there's a complete calculus definition for it, but it's like three-dimensional rate of change. Like with electromagnetic waves, you'll see gradients come up in Maxwell's equations. You'll see gradients come up because the electric field progresses in 3 dimensions. It progresses in a sphere, essentially. So that's kind of that. So for each point, so let's say that we wanted to get here. Let me show you another example of Perlin noise. Let's look at this. So what is this? It's kind of a shitty example. I'll get a better one. So Perlin noise. Usually you're going to see it in something like this. Now what is this? This is two-dimensional Perlin noise. And what it does is this is actually a height map. So it creates a height map using this algorithm that will then be translated into a mesh that looks something like this, or a mountain. The thumbnail of this is in Minecraft. Minecraft uses this as a generation technique. It uses something like this to place its block, exactly like this. This is 3D Perlin noise. This is 2D. You might know of World Machine. I think that's what it's called. A World Machine uses an element called Perlin, and it generates 3D mountain. It generates very realistic looking mountains using the Perlin noise algorithm. So essentially, you have a bunch of XY points. Where was it? So let's look at this once again. So let's think of each point on this image as an X and Y coordinate. So 0, 0. Here, I'll just put this in one note. So we go from 0, 0 to, I think it was 500, 500. And some point here, P has an XY. You guys can't see that. I should write down a better spot. Right here. So this point here, P, has coordinates XY. So for each point, we'll say P, and then X, Y, Z. So we'll generalize this for 3 dimensions, because that's what we'll be writing one method for each 1, 2, and 3 dimensions. So for each point, P, X, Y, Z, what you're going to do is you're going to get the neighboring points on the containing interval, square, or cube. So in 1D, you might think of it as, here, I'll get another image here, 1D Perlin noise. This is 1D Perlin noise. So for each point, there's some interval that contains that point. Yeah, exactly, right here. Like, let's say we wanted to do, for this image right here, where did it go? Here it is. So for this one right here, 1D Perlin noise, let's say we had 3.5. The 2 points that we would want to get is 3 and 4. On a cube, 3D Perlin noise, we want to get a surrounding cube around a point. So I'm just going to do 2D just because it's easiest to show right now. So on the interval, square, or cube, depending on the dimension. Now what you're going to do is after that you're going to calculate something called a gradient. So we talked about that real quickly, but there's a gradient for each of the neighbors. And And it's important that these neighbors, that the gradients have a specific way of calculating them. There's a set number of possibilities for the gradients. So in 2 dimensions, or in 1 dimension, you can only have 2 possibilities, up or down, right? Or there's a couple more, but there's a finite number of gradients that you could possibly have. So you have to have some way to fairly and evenly select a gradient for each neighboring point. And what you will then do is you will calculate the dot product between, or the dot product of the gradient. So calculate each dot product. So we're going to calculate the dot products multiple. So the dot products of the gradients with the distance vector. And the distance vector will be the subtraction of p of the point minus that neighbor. So this is going to be p minus, I'll say q. Alright, so these will be q here. So p minus q. So each neighbor is q or whatever, and you just get the dot product for g of q, and then p minus q, so the dot product between the two. And like I said, the gradient is a derivative of vectors, so it is a vector itself, so you can get the dot product between it. Now the next step is going to be calculating a weighted average. So step 4 is calculate the weighted average in each dimension and that's the final answer. Or here, I'll just say calculate a weighted average, and then that's the final answer. And the reason why I'm not giving any more details right now is because this is where the dimensions really differ. So I'm gonna go over this for each dimension. So we'll start in 1D. So let's say that we had a point P, and it was just 3.5. So first, neighbors are going to be 3 and 4. So I'm just going to use this kind of array notation here, just to show the neighbors. Now what we'll want to do is want to get the gradients. So g of 3, g of 4. Then the third thing, or here, let me actually just diagram this out. So let's say we had a number line, and we had P, and then we want to get 3 and 4 as these surrounding points. So the third step is taking the dot product of the gradients with the distance. So the distance would be something like that, and something like that. So P minus 3 and P minus 4. So now we're going to get the dot product. So we'll say G of 3 dot P minus 3 and G of 4 dot P minus 4. Like that. And now for the weighted average, we're going to have some constant for each dimension. So I'll say S is our constant, and I'll say Sx for the since we're working in the first dimension right now. Now S of x, and the way we will get the result here is through linear interpolation. So I'm going to call this LERP. LERP is equal to, I mean, it's kind of, so it's going to be, there's something here about it. So we essentially just take a weighted average of the two dot products. So let's call this dot product here, this is D1, or D1, and this dot product is D2. Now we have our constant S of X, or Sx, and our average, or the linear interpolation, is equal to D1 plus S of X times D2 minus D1. Just like that. And that's our answer for one dimension. Alright. Now, what is S of X? So S of X will be the result of a fade function, and a fade function meaning like some sort of smooth function. So fade, where we pass in the decimal value of x, so x modulus 1 or something like that. And our fade function, here I'll just diagram right here actually. Or what's our fade function actually? There was a link on for Wolfram Alpha here. Where is it? Here we go. This is it. So this is on Wolfram Alpha, and our fade function is this function right here, and you'll see that we'll get a value for each decimal. So let's say our decimal value is 0.5, well, we'll get 0.5 as the fade. And if it was 0.8, we'll get something around 0.95, something like that. But yeah, so then that would be our weight value, and then we'd get the result for the linear interpolation. Now for 2D, it's actually pretty similar, I'd say. So for 2D, we have our point, and I'll say 3.5, 6.3. Now what is this going to be? So we have our point here. Point like that, and we now have a surrounding square instead of an interval. So the surrounding points will be 3, 6, 4, 6, oops, 4, 7, and then 3, 7. So those are the neighbors. I'm not going to write them all of them out just because we have them. I just wrote them right there. Then they'll each have their own gradients. So something like that. And this will be coming out of the page, going into the page. It's hard to do in 3 dimensions. So gradient there, and then a gradient there. Now, the distance vectors are going to be the exact same. They just point from the neighbor to the point. I'll actually get the animation, or not the animation, but a good image for this. Right here. So this is these are the gradients, and these are the distance vectors. So we essentially just take the dot product between each of them. We get some results, and then now we're going to linear interpolate for each dimension. Now what does that mean? So we first, I'll just label this, I'll say D1, or this is 0.1, 0.2, 0.3, and 0.4. So we're going to linear interpolate for each dimension. So we'll start in X, and then we'll go to Y. So we still have an Sx, so S of X is equal to fade of 0.5, and S of y, now we have two constants, is equal to fade of 0.3 because that's the decimal value. So we're going to have our first linear interpolation, so I'll say L sub A is equal to d1 plus s of x times d2 minus d1. So this is the exact same thing that we have in the first one. However, we're going to have two linear interpolations in the x dimension because there's two sides for it. We have three, it's a square, so that you have two possible, or two neighbors, or you have two x pairs. So then LB is equal to d4 plus s of x, same constant, then d3 minus d4, or the other way around. And then finally, the result is lerp is equal to, now we're going to linear interpolate between these two using the y constant. So LA plus SY LB minus LA. And this is our final answer. Just like that. And finally, let's go into 3 dimensions. I'm not going to be able to draw much of this out because it's actually pretty complicated in 3 dimensions. So 3D, let's say we had a point 7.2, 6.18, and then 9.3, just like that. So now we're going to have 3 constants. So Sx is equal to fade of 0.2, Sy is equal to fade of, I'll just keep it at the same numbers for the dimensions. 3.5, 6.3, and then 7.9. And then Sz, so the constant in the z direction is fade of 0.9. And these are all using this same fade function here. What song is this? I don't remember this. Oh, I probably just have never heard it. Oh, this is a good one to just chill out to, so I'll skip it for now. Alright. Okay, so now in 3 dimensions, I can't really draw it out, but it's pretty obvious that we'll have 8 neighbors now, because a cube has 8 points. So we have n1 to n8. We'll then have g1 to g8. Then distance 1 to distance 8. And then we'll have dot product 1 to dot product 8. And what we'll do now is we'll do the exact same thing. So it's essentially we're nesting linear interpolations. So we're going to do the exact same thing like we did in 2D, which is the exact same thing that we did in 1D. So we'll get one linear interpolation is equal to d1 plus sx d2 minus d1. I should just replace these numbers. And we'll do this for all 4 pairs of x values. So LD is equal to D7 plus SX D8 minus D7. And then now we have 4 values. So we'll linear interpolate again, but this time we're going to be doing it in the y direction. So it's kind of like the how do I want to explain this? It'll make more sense in the code. So then we'll go LYA is equal to LA plus our y constant, then LB minus LA. And the same thing for C and D, so LYB is equal to LC plus SY, then LD minus LC, just like that. If you don't know what this formula is, it's just linear interpolation. It's a function that takes in 3 parameters. It'll make a lot of sense in the code. So this is our second nest. So this is one nest, and then finally we have our third, our final result, which is lerp, or the final answer is equal to LYA plus SZ. So the Z, so we're going into the third, the third dimension now. So we're using our third constant, and then we're doing LYB minus LYA. Alright? And then that's going to be our final answer for the 3D Perlin noise. So it's intuitive, because it's kind of like you're nesting, because in 3D we do elements of 2 dimensions. Like when we go between x, when we go in x, when we do the linear interpolation for the x values, we are doing the same thing that we did in 2D, and then we combine them like we did in 2D with another dimension constant. And then in 2D, we did exactly what we did in 1D, which is we did it for 1 dimension. So it's all kind of nested, but it all makes intuitive sense. Okay, now, I actually just remembered I wrote something down that made this make a lot more sense. So in 2D, lerp is equal to the function lerp, or our final answer, so the average, I'll say, is equal to lerp of sy, then our second parameter is 1D lerp top, so for the top x values, and then 1D lerp bottom. So the top x values being these two, and then the bottom x values being the bottom ones. And then for 3D, the average is equal to lerp of SZ of 2D lerp for the front, and then 2D lerp for the back. So that's kind of the nest. And then this thing will be inserted into there for the front and the back, etc., etc. So we will see how this all works, and we're going to get in the code right now, actually. Let me just take a sip of water first. If you were wondering what Ken Perlin, what the dude actually looks like, I got a picture for you. It's this. It's this guy. If you don't know who this actually is, it's not Ken. It's Kenny from the B movie. What Ken Perlin actually looks like is this. I zoomed in a lot. This is his homepage on NYU, and he does a lot of cool stuff actually. And he's still teaching at NYU, which is he's teaching computer graphics at NYU, which is cool. Yeah, so he does a lot of stuff, and it all makes, and this is one of his most famous algorithms, because it's been adapted ever since. So, all right, now let's start writing some code. So the first thing I wanted to do was I wanted to take a library that we wrote last time, the image library, and just put it in to our code here, because we are going to need it. So I put the link to the files down below, or to one of the files down below. but you're going to need image.hpp and then also bmp.h, so both the header and the source file. So just go ahead and copy those over. Because we're going to be what we're going to be outputting today is 2D Perlin Noise. And we'll be outputting it as a height map, like we've seen. And the way to do that is we'll do that through a bitmap. Now I did make a couple of changes to the bitmap library. Oh, I need to make sure I pulled that stuff from the... Okay, I think I did. I can actually check, but there were two changes that I'll talk about right now. So the first one, let me just I'm just going to include them in the project. So the first one was this conversion in set pixel, where we pass in doubles. When someone called this, so I'll talk about what we're going to be calling this, because the Perlin Noise algorithm outputs a value between 0 and 1, so a double value, and we'll just be converting that to a color. When we call this, this calculation here, r times 255 plus 0.5, outputted as a double. So what it was doing was it was calling the exact same method, because it wasn't finding the bytes. It wasn't interpreting it as a byte, because the calculation just outputted a double. So it was causing a stack overflow. So what we have to do is we just have to create an explicit conversion to byte, so it calls that method there. And then I also screwed up with the calculation for the padding. I just had 1 4 minus in there for some reason, don't know why, but that was the other mistake. So it's all updated on the GitHub, so you don't need to look at it. Okay, so now let's actually start writing some code. So in main.cpp, I'm just going to go ahead and do our classic hello world stuff. So include iostream int main standard cout hello Ken. Alright. Okay. And we'll be creating this as a HPP file, just because I really like those, because it's easy to distribute. So in Perlin.hpp, we're going to start off with a couple of includes. So we'll first our macros actually. So if not defined, Perlin HPP, define Perlin HPP, and diff. So for includes, we're going to say include iterator, include algorithm, include random, and that's that. I'm going to put this in the namespace once again, so namespace Perlin, and we will start out with utility methods. Alright. So for the utility methods, we're going to start with something called a fade function. So this is how we get our the weights for each dimension. So fade function, and this is just going to be of the form f of t is equal to 6 times t to the 5th minus 15 times t to the 4th plus 10 times t to the 3rd. If you were wondering why this function is the way it is, well, the main thing is you want it to go between 0 and 1, between the range 0 and 1. So like this. So from 0, you just want it to end, kind of stay in the square here. But there's also some things about it having a derivative at 0 points in certain places. So at integer values, it's going to have a 0 derivative. And yeah, I should actually enlarge this just so. Oh no, I need pro. Okay. Well, anyway. Okay. So the way we're going to do this is we're going to kind of optimize it for fewer multiplications. So we're going to be writing it in a form that doesn't multiply as many numbers because that's a taxing operation. So we're going to say for the function inline float fade and passing the float t. You might be wondering what the inline is. Well, it allows the namespace to kind of have something like a static method. So this is something that I didn't do on my previous libraries, like in the JSON library. I never had the inline and it caused problems. So I updated it, and inline actually allows the compiler to not define it several times. So the way we're going to do this is just return t times t times t times, that make sure that you're doing this exactly in this form, and then in parentheses t times another set of parentheses t times 6 minus 15 close one set of parentheses plus 10 close parentheses and then semicolon. So this function right here, if you expanded it, it would become this polynomial right here. Next we're going to have our linear interpolation formula. So linear interpolation, or LIRP for short. So this function is just x of t. Here I'll just write it out actually. So inline float LIRP, you pass in a float t, float a, and float b, and we're going to return a plus t times b minus a. So we are essentially interpolating between two values. Maybe and this formula only applies for between two values, and it's kind of just like going. It's assuming this kind of slope, or this constant rate of change between a and b. So like I can draw this out over here. So let's say we had a function f of x here. And then our x values were a and b. And then this was that, and that's that. So f of a and f of b. So this formula assumes some sort of linear rate of change between the two, so a constant rate of change. It's like a line. And what t is the proportion that it wants to go through. So let's say t is 0.5. Well, then you would go to the middle. T is 0.75, 3/4 of the way. If t is 0.1, you go 1/10 of the way. If t is any number, you just go that portion of the way. So that's how linear interpolation works. Alright. And then we're also going to have a map function. So this map function, it just allows you to map one value in one range to another range. So inline float map, float val, float OG min, float OG max, float new min, float new max. And I'll also diagram this out. So the way I kind of created this was, let's say that we had a number line. Oops, I can't draw. So OG min sounds like a name, and then OG max, and then new min and new max. And let's say that our value was right here. So it's going to have some proportion. So From here to here is some proportion. And it's going to be equal to the val minus OG min over OG max minus OG min. And then we essentially want to translate this proportion to this new range. So it's going to have the same sort of... God damn, I keep getting distracted. So we want to translate this proportion, so that I'll call this P, and we just want to have it mapped to this new range here. So that the new val minus the new min over new max minus new min is also equal to P. So that's kind of how that works. So it's as simple as just going get proportion in original range. So float prop is equal to val minus OG min divided by OG max minus OG min, and then we just return new min plus proportion, or we can honestly call linear interpolation here. So return lerp, the proportion of the way is prop, the minimum is new min, and the max is new max. So that's kind of, yeah. This is another application for linear interpolation. And we'll be needing this function to map the result of the Perlin algorithm. Okay, a final utility function is going to be our gradient function. This function will calculate the dot product between the gradient vector and position vector, or distance vector. So inline float grad will pass in an integer hash. So the hash will kind of tell us what gradient to use, because it's going to be like a pseudo-random gradient. And then the point, so float x, float y, and float z. So in his original algorithm, this was kind of condensed, but I'm going to try and explain this as best as I can. So we essentially want to, in this function, we want to convert the last 4 bits of the hash into one of 12 possible gradients. So we're going to say int h is equal to hash bitwise and 0b1111, and this is equal to hash and bitwise and 15, which is equal to hash modulo 16, that's just a trick, which is also equal to getting the last 4 bits. Because if you and a bit with 1, you get the original. If you bitwise and 1 bit with 1, you get the original bit back, because 0 and 1 is 0, and 1 and 1 is 1. So now we're going to be essentially traversing through each bit to determine which gradient to use. Now, I'm gonna draw this out, or I'll kind of write a little bit. I didn't understand this function too much at first, but I eventually did. So in all 3 dimensions, the possible gradients, so the gradient will be of some form 1, 1, 0, or -1, 0, 1, something like that. And it will go, and these will be the 12 possible gradients or whatever. Now, if the position, so let's say that we had our point x, or not our, the distance. So let's say dist vector was dx, dy, dz. The dot product between the distance vector and a gradient would just be, so we're going to return 1, or, gx times dx plus gy times dy plus gz times dz. That's just dot product. That's just a regular formula. Now, the hash will determine 1, which components to use, and 2, what sign to use. Because if you look at these, you'll see that a common theme is that there's always going to be at least 1 0 in there. Or that's not always, sorry. But if the hash, if it's determined that there should be a 0, that component will just be here. So let's say that our gradient was -1, 1, 0, and our distance was equal to 0.6, -0.7, and -0.1. The dot product here, -1 times 0.6 plus 1 times -0.7 plus a 0 times 0.1. So what you'll see is that the z component goes away, and both of these components are negated. So we get a -1.3. And that's just the dot product. And then we'll use that to linear interpolate, so on and so forth. So we're going to be selecting that gradient vector very carefully based on the hash value. And from that gradient vector, we determine which component to use and whether or not to negate it. So, and you might, and if you're doing some other research, you might have seen how you could have a table of gradient values, and that would be the exact same, except you wouldn't have to go through this kind of selection process. But it does make a little bit of sense. And this is pretty much directly from his original algorithm, just with a couple of extra comments. So, first condition, if the first bit is 1, set to x, otherwise set to y. So float u is equal to h is less than 0b 1 0 0 0 question mark x colon y. So this means if hash is less than 8, set u to x, otherwise set it to y. And this means that if the first bit is 1, it will be greater than 8, greater than or equal to 8. Otherwise the first bit is 0, so it will be less than 8. Now if the first and second bits 0, set to y. If first and second bits 1, set to x. Else set to z. So float v is equal to h is less than 0b 0 100 question mark y colon. Now we're going to go into another if ternary operator. H is equal to 0b 1 1 1 0 0, or h is equal to 0b 1 1 1 0 question mark x colon z. So this first one here, if h is less than 4, that means that both bits are, the first 2 bits are 0, so set it to y. Now if the first and second bits are 1, which is either 0b1100 or 1110, set it to x, otherwise set it to z. And then essentially we want to say make u and v negative based on the last 2 bits, then add results. And adding the results is like dot product because gradient components are just one. So the results of dot product is adding distance components. So that was another thing that I had to work on. Since we're only going to be multiplying by ones and negative ones, it's just going to be the distance component. So we'll just be adding, subtracting, whatever. So we're going to say return in parentheses h bitwise and 0b0001 is equal to 0, question mark u or negative u. So if if the last bit is not 0, if the last bit is 0, set it to u, otherwise set it to negative u. And then add that to same thing just for the second bit. So h and 0b0010 is equal to 0 question mark v colon negative v. So it's just like a dot product there. And you actually see that these are the dot products. Like we're adding u and v, and u and v are x, y, or z depending on what the bits are. Alright. So those are the utility functions, and next we're going to get into the main class. So I'm actually going to go refill my water before we get into this, and then we'll just plow right through it. Well, I am really sorry about that. If you had headphones on, I just dropped my microphone. I am really sorry about that. Oh no. I just tugged on the wire with my leg because I sat on it. Oh no, I'm really sorry about that. God damn it. Jesus Christ. That must have been painful. Okay, I'm gonna try and not knock this anymore. Alright. So, let's get into writing this. Alright. I should just switch back to the desktop. Alright, so we're gonna have a class here. And then we'll have some private members. So the first thing is our permutation table. So unsigned char p, and it'll be of size 512. So this will be our pseudo-random permutation table, and this will be where a lot of the degree of randomness comes from, not just this table, because we're going to be shuffling it using a seed. So unsigned int seed, and if you have ever played a game like Minecraft, you generate worlds using seeds, and that seed is deterministic of how the world looks like, because that seed determines what the height map looks like, or what the 3D Perlin map looks like. Minecraft uses Perlin Noise based on the seed that you give it, so it generates those worlds based on that seed, which is really interesting. Okay, now for public, let me actually just minimize these on my computer so I don't have everything in here at one time. Oh, funny story I wanted to talk about. I was doing some landscaping work at the local cemetery, or the cemetery near my house. And I was moving rocks, and you should have seen with a wheelbarrow. And as I was moving the rocks like into the dumpster or whatever, because I had to move them from a pile in a dumpster, or in a wheelbarrow to a dumpster. And I probably discovered like 3 new species of bugs. There was the like 103-peed as opposed to the centipede. I found so many fucking centipedes in there that just make. Then there were fat too, like fat centipedes. It was just not fun. God damn. Okay. I don't want to think about it. All right. So we'll have a constructor / modifiers. So the constructor, Perlin will pass in an integer seed, or unsigned seed, and then we'll have a method to reseed the class. So void reseed unsigned int seed. Then we'll have the actual Perlin methods. So we'll have one method for each dimension, so 1D Perlin Noise. So void noise, or float rather, float noise 1D, float x, 2D Perlin Noise, float noise 2D, float x, and then 3D Perlin Noise, float noise 3D, float x. And you'll see why we're separating them into by their dimension, and it's just based on computational capacity and unnecessary resources. All right. Let me actually just check something real quick. I just need to make sure that the mic is all right. The mic is still transmitting. It's all good. Okay, so let's start with noise 1D. Okay, so the first step is we're going to be finding the interval containing points. And this will just be the lower points, so smallest points of interval containing target. So I'm going to say integer xi is equal to the integer value of standard floor f of x, and then we're going to bitwise end it with 255. This is equal to the modulo of 256. And you'll see why we're doing that in a bit. Next is going to be, we're going to be getting the decimal value of each component. So x minus equals standard floor fx. That's relatively self-explanatory. You just subtract the integer component and you get the decimal component. Now we want to get the smooth noise, or get the smooth value from fade function. And this becomes the weight for each dimension. So for 1D, we'll just have 1, which is just float u is equal to fade of x. And once again, fade goes from 0 to 1. Now we're going to here, let me just look at my comments here. We're now going to get the input or the hash value for all the neighboring points. So get hash value for all neighboring points. So int a and b. So a is equal to the permutation table of x, xi rather, and b is equal to the permutation table of xi plus 1. And I realized I forgot to do that, the permutation table setup, so we'll do that right after this. Not many more. So these are just the hash values. Now we're going to get the weighted average. And we're going to say float average is equal to linear interpolate. The weight value is u. I'll call it s of x. The first value is going to be the gradient of a, x, and 0, 0. Then the gradient value of a, x minus 1, 0, 0. So for the gradient function, you can pass in zeros for the dimensions that we're not using, but you could also do that for the noise. Like for noise 1D, we could call noise 3D with the x value then 0, 0, but it would just use a lot of resources, whereas with the gradient, it doesn't take up that many, so we can just use 0, 0. The reason why we're doing x minus 1, I remembered this for a second. The reason why is because the distance, so when we look at, let's look at back at 1D. So the distance from p to 3 is positive. So p minus 3 is going to be a positive vector. However, p minus 4 is going to be a negative vector. So anything greater than the point will have a negative value. So we want to subtract 1 from the decimal. And because we're just looking at distances here, and we know that the unit interval, unit square and unit cube will have dimensions of 1, we can just subtract 1 from the decimal component and get the value of the distance vector in that direction, or in that dimension. And then we're just going to, now we have to return the average mapped from -1 to 1, and we're going to map that to 0, 1. Now the reason why we have to do this is because this algorithm theoretically returns a value from -1 to 1. And I'll actually test that, but we'll see how it looks. And then we'll just say return map average -1, 1, 0, 1. So the map function that we wrote, we just get a value in between -1 and 1, and then we map it to a new interval. Okay, now let's actually do the modifiers up here. So for the constructor, it's as simple as just calling reseed with seed. Let me just make sure of that. Yeah, we're just calling reseed with seed. Now for reseed, what we want to do is we actually have to say seed is equal to seed. So set the seed in this class to the parameter. And then now we're going to populate the array in order. So populate permutation table in order. So for unsigned int I is equal to 0, I is less than 256, I plus plus. P at I is equal to I. Now we want to shuffle it. And this is where our seed is going to come into play. So we're going to say standard shuffle, standard begin of P, comma, standard begin of P plus 256. And then the seed will be standard default underscore random underscore engine seed. So what is this function? So we're calling the shuffle function. We're going from begin to begin plus 256. Now, why am I not just doing standard end of P? Well, the reason is P, or oh wait, it's not P. Oh, it is P. So P has a size of 512, and they're all set to some null value, I think it is. So if I were to shuffle from the beginning to the end, I would be shuffling in the 0 to 256, but then also the null values. So that would be kind of ruining the purpose of the shuffle, or of the overflow rather. So I want to go from 0 to 256 and only shuffle those. And then now we want to duplicate array for overflow. And the way to do that is just for unsigned int I is equal to 0, I is less than 256, I plus plus P at 256 plus I is equal to P at I. All right. So fun. And the reason why we want to have overflow is because this value here could exceed 256 when we add 1 to it, because we're getting the remainder, but if we add 1, it could be a border issue, so it will then cause that. Alright, now for 2D Perlin Noise. It will look very similar, just more values. We'll have more variables. So this time we want to find smallest point of square containing target. Oh, noise 2D has to have float y as a parameter, and then noise 3D will have float y and float z. I didn't put that in. Okay, so we're going to say int xi is equal to the integer value. Actually vary this the exact same as above. So you can actually just copy and paste this real quick, and just then do the same thing for y. So float or integer yi is equal to the integer value of floor, the flooring of y, and then bitwise and with 255. Now we want to get the decimal value of each component. So x minus equals standard floor fx, and y minus equals standard floor fy. Next we want to get the smooth value, or get a smooth value from the fade function. It becomes the weight for each dimension. I'm just going to be using pretty much the same comments actually. So this time we're going to have 2, so float sx is equal to fade x, and float sy is equal to fade of y. Hold on, I just got a text in a second. Oh, Jesus. That's a lot of text. Alright. Sorry about that. Oh, this is a slapper. Okay. Now, once again, we're going to get the hash value for all neighboring points. So this time we're going to have 4 of them. So int AA, AB, BA, and BB. I should have actually created a paste bin for this. This is going to be super annoying. Okay, so AA is equal to P at P at XI plus YI. Exactly like that. And I'm putting the spaces just because it's going to line up better. Then AB, BA, and then BB. So rule for here, if there's a B, just add 1 to the X or Y. So in AB, it will be, instead of YI, it will be YI plus 1. And then do that for the X. And then for BB, both of them have a plus 1. And these plus 1s are just from the neighboring, so we can get the neighboring points. And I should actually, I haven't run this problem, but I don't, oh yeah, so I also wanted to say this is why we need the overflow. Because the maximum that P of Xi can be is 255. And the maximum Yi can be is 255 because we bitwise ANDed it here. So 255 plus 255, that maximum will be in the permutation table. Now we want to get the weighted average. So here we're going to say float average is equal to lerp. For the outer lerp, the constant will be sy, and then our first point will be another linear interpolation. I'm just actually going to set it up like this. So our constants for the 2 inner interpolations will be sx, and the first one will be our top, and then the second one will be the bottom. So this is pretty much what I said in the OneNote, or drew out in the OneNote, and we're going to be nesting these essentially. So we do a 1D linear interpolation for the top, and then 1D linear interpolation for the bottom. So we're going to say for the first parameter, for the top, we're sx, and then gradient. We're going to pass in AA for the hash, then x, then y, and then 0, because once again, if you don't have the component, you can just pass in 0 for the gradient. Then gradient, AB, x minus 1, y, comma 0. And then minus 1 is for the same reason, because the distance will be negative. You know what, let me actually just draw this out, because I don't think I've explained this. Where did my pen go? My pen on the floor somewhere? I'm actually bungled. Where did my... Where is my drawing pen? blind. Oh, it's right here. It's the keyboard. Alright, good. So let's look at a square real quick. And let's say we had our point here, P, X, Y. This one will be A points XI, YI. This one will be BA with points XI plus 1 and YI. Then top right is BB, not BB8. And this will be XI plus 1, YI plus 1. And then the top left is going to be AB, XI and then YI plus 1. So the distance vectors will look like this. This is going to be a tough one to draw. Oh, sweet and perfect. And the components of these vectors will be from here to here. We have I can actually just draw this on the dotted lines because the components are shared pretty much. So from the point at the top, it's going to be y minus yi, which will convert to yi minus 1. Then here we have x minus xi. The one to the left is just x, and the one to the bottom is just y, because they're the decimal components. Or wait, this is x minus 1 and y minus 1, I'm sorry. Yeah. Okay. Wait, no, I'm sorry. Or, you know, it works out. I mean, that's just the explanation for the subtractions in there. If you didn't really understand why that was. I keep knocking my microphone, I'm sorry. Okay, and then pretty much the same thing for the bottom linear interpolation. So gradient of AB, x, y minus 1, 0, and then gradient of BB, x minus 1, and y minus 1. And you'll, in the 3D especially, we'll see patterns for what is minus 1 and what isn't. And it actually directly correlates to what the hash values were. Okay, now for the big boy, for noise 3D. So this is going to be the big push, and we're going to have a lot of values here. So once again, we want to find smallest point of cube containing target. So integer xi is equal to the integer value of standard floor f x bitwise and with 255. Do the same thing for y and z. What I like to do with these is I just like to, on Visual Studio Code, or Visual Studio at least, I like to do Control D just to copy the line, which is pretty good. And then you can just modify the values. Now we want to get the decimal value of each component. So I'm actually just going to copy and paste from the 2D. I'll just add a z. So z minus equals standard floor f z, and then float s z is equal to fade of z. Now, if you wanted to be really clever, what you could do is you could do a reverse nest where you kind of called the previous ones from, so like in noise 3D you would call noise 2D, which would call noise 1D. Maybe we'll look into that, but I don't want to go too long, so I probably won't do that, but maybe I'll add that on as a little challenge. Now, once again, you get your smooth values for the weights, and then we want to get our hash value for all the neighboring points. Oh, I did forget to return a value in noise 2D, so just remember to return the mapped value. It's the return will be the exact same for all three. The return line will be the exact same for all three dimensions. Now we're going to be getting the hash value for all the neighboring points once again. This time we're going to have 8. You can actually make, I did make, what you could do is you could make these hash values unsigned char, because the permutation table is actually unsigned char, which then allows you to make the parameters for the gradient, the hash, make it an unsigned char, but you don't have to. You can keep it as an integer. I'm just saying that you could do that if you wanted to. Could you? Yeah, you could. Okay, so hash value for all neighboring points. There's going to be a lot of them. So unsigned char, AAA, ABA, AAB, ABB, BAA, BBA, BAB, and BBB. Okay, you know what? Screw this. I'm going to create a paste bin for all of these. Just give me half a second, because this is getting a little annoying. I don't want to have to write them out. Alright, so paste bin. Perlin Noise hash values. All right. On to 2D. And finally 3D. These 8 ones are not that alright, create new paste. I am now going to copy it and put it into the, oh my god, not, god damn it. Hash value paste bin. Alright, so the link is saved, and now should be good just to take it from the paste bin. So I put that up there and just take it and put it into the program. Unfortunately, it doesn't take spaces, which is, you don't have to have spaces if you don't want to, but I'm going to, just because it makes things look a lot neater. Alright, perfect. Alright, so there are 8 hash values, and now we're going to do the weighted average once again. So we're going to say float AVG is equal to linear interpolate. So we'll start with so the weight is going to be SZ, and then we're going to linear interpolate for the front, and then we're going to have another linear interpolate for the rear, or the butt of it. In front, we're going to have pretty much what we have in 2D. Once again, I like the way that I wrote this out, but you could also call the previous ones, which I will leave to you as a challenge. So the weight is going to be SY, then lerp SX, and then the gradient values AAA X Y Z. I'm sorry, but I should also put this in the paste bin. I should. BAA, then X minus 1, Y, Z. You'll see the patterns for the X minus 1s and whatnot. So I'm just going to copy and paste, follow along, because if you listen to me, you might go crazy just as I am. But once again, you will find patterns. Like for each dimension, the values will always cycle the same. So once again, we have our front top, then the front bottom, and then the same thing pretty much for the rear. So we're going to be using the same weight, SY. Then instead of having A for the, so in the front, the Z will always be A. However, for the rear, the third character in our hash will be B. And then what you can also do is just change all of the Z values to Z minus 1. And then the last one should have all of them being X minus 1, Y minus 1, and Z minus 1. Okay, and then finally we want to have that same return statement. So return map from -1 to 1. Here, I'll zoom out for a second and let you guys. So this is the weighted average for 3 dimensions. Pause the video, honestly, if you need, because this will also all be on the GitHub if you just want to copy and paste, and that'll also be fun. Okay, so now we can actually go ahead and test this. So let's look at how this will look in main. So in main, we have to include our image in Perlin. So include image.hpp and include perlin.hpp. We're going to initialize our Perlin, so Perlin Perlin map, and I'll have a random seed. You can just type in anything, so long as it's under 2 to the 32 minus 1. Then we're going to have our image, and image.generate, and I'll say 512 and 512. So this method just create space for a 512 by 512 image. Now what we're going to do is we're going to iterate through each point. Or first we have to get something called a frequency, so double. And this will be kind of like the repetition, you could say. So I'm just going to set it to 8 for now. So double fx is equal to image.getWidth divided by frequency, and double fy is equal to image.getHeight divided by frequency. Now we're going to iterate through each point, so 4 into y is equal to 0, y is less than image.getHeight, or I'll just say 512, y plus plus. The same thing for x, so for int x is equal to 0, x is less than 512, x plus plus. Then we want to get the double value, so double p is equal to map dot noise 2D, because we're doing 2D noise, and we're going to do x divided by fx and y divided by fy. So this frequency value will just add more variation, and I'll also show you what it looks like without it. And then all we want to do is set the pixel, so image.set pixel x, y, and then p, p, p. And then after the for loop, we just want to write, so image.write out.emp. Alright, now we can go ahead and run it for the first time, and we'll see what we get. I hope we don't get any errors. And alright, it ran pretty fast actually. So reload, and we get this sort of thing. I hope that actually might be an issue, because you know, let's try it without the divided by f of x and divided by f of y. So just do x and y. And you'll see that it's just gray. And the reason why is because x is just an integer. And integer values have no decimal values, so the fade function will be 0. The weight for each dimension will be 0, and then you'll just get the constant value for every single weighted average. I don't know why it's giving us that, like, I hope that's just a bug that happens now. But that doesn't, no, that just doesn't look right. I don't know. Okay, there might be something wrong. Okay. But anyway, that's not that interesting. You know what, let me just test something here. I'm gonna go I'm just going to test this on my second screen right here, just so I can determine if that is a bug that has to be fixed, or if that's normal, because I haven't seen that before. That's something that that is abnormal, I'd say. Although what you will notice is that it does have 8 it's 8 by 8, so that's where the frequency kind of comes in. Hold on just a second. Okay, I'm running it on my other computer right now to see what happens. Alright, it's running. No, that's wrong. Okay, there's something up with it. Because I'm getting something that looks like Perlin Noise without the squares. So, alright, let me just go through this. Alright, so Noise 2D. Alright, you find xi, standard for f of x, y, bitwise and with 255, x minus equals, get your weights from the fade function, proper hash values, AA, AB, BA, BB, that is right, and for the interpolations. Oh, I know why. Wait. Oh, yeah, because make sure that so in 2D, instead of you should have the two parameters as AA and BA for the top. So when you're in one dimension, only that letter should change. So when we're using the weight in the x dimension, the x character should go from A to B, no other one. And then in the y direction, the character will then go from A to B in the second character. So when we're only in the x, like right here, I'll zoom in. The gradients, I'm in Noise 2D right now. It's AA right there. Or for x, it goes from A to B, but y stays constant. However, when we go for the second parameter in the y direction, we go BB, AA to BB. Okay. Now I hope this works. Let me just make sure that I didn't screw that up anywhere else. Yep. Okay. Now it's right. Now let's run it. And okay, so that looks a lot better. So this is one iteration of Perlin Noise. Doesn't look too interesting. It's kind of blurry, and there is one kind of add-on to this called Brownian factorial notion. Brownian, I forget what Brownian fractional Brownian motion. So this is kind of an extension of Perlin, and it kind of accumulates Perlin results. So it's going to be accumulated noise. That's going to be what we're calling it. So we're going to have, we'll just do 2D for now, and then I'll just leave the 1D and 3D to the GitHub because they're the exact same. I just don't want to take too long here. So 2D accumulated. So still returns a float. And we're going to say accumulated 2D noise, or accumulated noise 2D, passing float x, float y. Int octaves is equal to 8 by default, so this is just the number of iterations. There's going to be something called a float lacanarity, I don't know, and that's going to be equal to 2.0 float, and then float gain is equal to 0.5f. So I'll explain what each of these mean as we're writing code. So float result for placeholders is equal to 0.0 float. Float amplitude is equal to 1.0 float. Float frequency is equal to 1.0 float. and then float max val is equal to 0.0 float, and we're going to need this to normalize the result. Normalize. So we're going to go through each octave. So for empty first condition, octaves is greater than 0, octaves minus minus. We're going to get another result, so iterate through the Perlin Noise algorithm once again. So result plus equals noise 2D, x times frequency, y times frequency. Those are the parameters, and then multiply that result times the amplitude. Then we want to add the amplitude to max val. Then we want to change the amplitude and the frequency. So amplitude times equals gain, and frequency times equals lacinarity. I'm gonna look up this. Lacinarity. Pronunciation. Hold on, let me pause this music real quick.
Lacunarity.
Alright, lacunarity, okay. And then finally, we just want to return the normalized result, which is just getting it between 0 and 1, so return result divided by max val. So the reason why this is normalized is because, and why it's between 0 and 1, is because the maximum value that each iteration will produce is from 0 to 1. Now 0 to 1 times the amplitude gives us 0 to the amplitude. So the maximum value will be amplitude, so we just want to add amplitude to the maximum possible value for the results. So we just divide by that maximum value to get between 0 and 1 for the entire thing. So now let's use this. So we'll say map.accumulated noise 2D, and we'll just use the default values, and then let's run it again. And it takes a little longer, but not too long. Now out.bmp, and you see it looks more rigid, there's more detail, and if I kept going, and if I converted this to a height map, it would look like something like a mountain range, or it would look like a terrain. It would look like some sort of terrain, actually. So yeah, that's Perlin Noise. Now if that's all you wanted to know, good, you can stop the video here, but I'm going to try and actually do this for do that challenge that I wanted to do, and that was 1 second. Which is to call the 1D and 3D, or call the previous noise values or noise functions from the higher order. So let's start in 2D, because that's how we can know it'll work. Alright, so so what I'm thinking is we get 2 average values. Oh no, I don't think it's, no, it's actually not going to work. No, that won't work. The reason why is because we get the permutation values using both x, y, and then z. So it depends on all 3. So we can't. All right. I thought it could be really cool, but I guess not. Well, anyway, you want to you can play around with this. Play around with frequency. God damn it. If I wanted to make the frequency like 16, you'll see more features. So if I run this, ends, you'll see more features. And the stuff is smaller because it does stuff more often. if I wanted to add more octaves, so let's say 16 octaves. Let's see what the result looks like. I don't think that's much of a difference actually. But it just repeats it over. I think once you get past 8, like the difference isn't too noticeable, but there's just more, it just repeats the algorithm more times. Now let's go back to a frequency of 8, or an octave number of 8. Let's do lacunarity for let's do 1.5 float for the lacunarity. And you'll see it's a little more blurry. This is because if the frequency doesn't increase as fast, you're not going to see as many things. It'll be a little blurrier, so you don't see as many features here, but it does look kind of cool. And now let's try doing the gain, and you should see a relatively darker, nah, that's not, we'll do 2.0 float for the lacunarity, and then for the gain, I'll say 0.75 float, and we'll see what this looks like. And you see it's a little brighter. Now the reason why is because the amplitude doesn't decrease as fast. So if we, now let's try doing the other way. So let's make the gain 0.25. So it will decrease even quicker. Should be, it's a little darker. Well, there's more dark spots in there. So you see, you can play around with those variables, see what you like. But I mean, that's pretty much the algorithm. I don't know what else to say. It was an adventure to get through this, but it was fun. I enjoyed it. Yeah. Once again, any questions, post down below. I'll try and answer them with my puny knowledge, but I'll try. Don't know what I'm going to do Thursday yet. It's kind of procrastinating, but I don't know if my schedule is going to be changing in the near future. Probably just to 1 stream per week, or 1 coding stream per week and 1 gaming stream, something like that. But for now, that's pretty much it. Not much else. But if you do want to explore more, I can put some more links, because this stuff is I really like this. It's very cool. So yeah, that's pretty much all I have for you guys today. I will see you guys possibly on Thursday, probably on Thursday, but yeah. Anyway, I have said goodbye maybe 5 times now, and I'm gonna say it again. I will see you guys during the next stream.